So with that, I want to thank today's speaker, Megan Pickett, Associate Professor of Physics and Chair of the Physics Department at Lawrence University, for her willingness to be a presenter in this new forum. I also want to note that Megan was scheduled to present a Bjorkinen seminar this summer, and she is a beloved Lunch at Lawrence presenter, so she's presented for us for multiple events. If you have any questions for Megan, please submit them via the chat function, and we will have time for questions at the end of her presentation entitled The Faithful Beauty of the Stars. And now for our featured speaker, Megan Pickett.
Well, thank you so much. Thank you for that introduction, and thank you everyone for coming to this webinar. I start, as I have for the last term, sharing my screen. This is our reality these days. I want to start with a thought about a natural resource that we often take for granted, and that is the night sky. And I also want to take us back about 100 years ago. 100 years ago, astronomers were, in 1920, were just learning that there were other galaxies apart from our own. 100 years ago, the International Astronomical Union, the governing body of all astronomers, decided to lay out and formalize the 88 constellations and the names of stars that astronomers use. And 100 years ago, Sarah Teasdale wrote the following, one of my favorite poems, very deeply meaningful to me, called The Faithful Beauty of the Stars. I went out at night alone, the young blood flowing beyond the sea seemed to have drenched my spirit's wings. I bore my sorrow heavily. But when I lifted up my head from the shadows shaken on the snow, I saw Orion in the east, burning steadily as long ago. From windows in my father's house, dreaming my dreams on a winter's night, I watched Orion as a girl above another city's light. Years go, dreams go, and youths go too. The world's heart breaks beneath its wars. All things are changed, save in the east, the faithful beauty of the stars. And the reason why this is something that's very close to me is that I have wanted to be an astronomer since I was just about 13 years old. Not quite 60 years after Sarah Teasdale wrote that poem, I myself stood outside our suburban home in Michigan, just outside of Detroit. I had been sick for about a week and a half with the flu, and my brother Galen brought home a book on the stars, and it was the first time that I had the opportunity to actually look at the constellations and try and memorize them. And I remember using punch cards that my father had brought home to make flashcards of the constellations. Even though we had lived in dark skies in the past in Denver, as my dad would always say, he would never get lost at night because wherever he looked, he'd see 7 Big Dippers. So it was up to me to figure out what was up there. And one night in December of 1978, I stood in the snow and for the first time could see the stars and see the constellations. And the first constellation that I saw was Orion, rising in the east. The book, in particular, was H.A. Ray's The Stars, A New Way to See Them. H.A. Ray and his wife were more famous, at least, still are, for the Curious George books. But the thing that made this book such a unique treasure and a continued treasure for many of us is that he took, as you can see with Gemini, the stars and erased the classical lines. The International Astronomical Union, full of good folks, all I'm sure in 1922, still decided to use sort of a spaghetti pattern for drawing constellations that ended up looking nothing like what they were supposed to look like. And so what H.A. Ray did, and what has worked for me and countless others, was to erase those lines and redraw the constellations so that they would appear more like what they're supposed to be. So you could see that with some of the more obscure constellations. You could even see that in something as well known as Orion. On the left, you can see Hevelius's version of Orion, which is, of course, an artistic depiction of the Greek mythological figure. On the right, H.A. Ray's version of Orion, which gives a little more sense of the figure that we're supposed to see in the night sky. You'll also notice that, as is the case with many star maps, that because you can't actually draw the brightness of a star, he used different sizes to tell you which stars were the brightest. And we'll come back to this. Astronomers use a system of brightness called the magnitude system. This was something that was invented by Hipparchus in about the 2nd century before Common Era. And it basically, his way of constructing brightness was to bundle all the brightest stars and call them 1, and then the second brightest 2, and so on, down to about 5. We've extended that with our own observations photometrically to negative magnitudes for very bright objects and very large numbers for very dim objects. Human eye can see down to about 5 or 6, depending how good your eyesight is. So that's Orion. And while I could spend hours talking about all 88 of my favorite constellations, I do want to spend today with you talking about Orion because of its importance and because of the way that we can use Orion to show our heritage in the sky and really appreciate, I hope, the night sky as a resource, not just a natural resource, but also a historical and cultural resource. The first indication, or the first noted depiction of Orion was about 35,000 years ago. It's on a mammoth ivory tooth carving in the Ach Valley in Germany. And while we know Orion, if you are familiar with Greek mythology, as a hunter, and his story in Greek mythology is attached to other constellations in the winter sky, every culture and every civilization has had a story and of special significance for Orion. The Sumerians called him Ura Anaa, which was part of the Gilgamesh cycle. The Babylonians called him Mul Sipa Zi'ana, the true shepherd of Anu. The Armenians knew him as Hake, their legendary founder. Indians called him Nataraja, the cosmic dancer, an avatar of Shiva. In Egypt, Orion was known as Osiris, and as well as Unas, the last pharaoh of the 5th dynasty. Aztecs saw in the belt and the sword a sacrificial fire. The Scandinavians saw Freya's staff. Hungarians called him Nimrod. The Chinese looked at the 3 belt stars and recognized them as one of the 28 lunar mansions in the celestial sky. And the Hittites knew him as the legendary figure of Adat. In North America, there were many stories associated with Orion. The Ojibwe people knew him as the Winter Maker. It is the constellation, the group of stars that would rise and tell you that winter was on its way. The Yokot people looked at the belt stars as the 3 footprints in the snow of the god of the flea people. The Navajo knew him as the first slender one. And the Chinook considered the belt and the sword, right here, as 2 canoes vying for a salmon in the Great River, which we know as the Milky Way. And for the Lakota, the belt represented the spine of the great bison. The rest of the bison included stars from neighboring Taurus and Gemini. So Orion was a central figure in much of the way we looked at the sky from many different people, and continues to be one of the brightest, one of the easiest star or groups of stars to see. And as I'll mention later on, it's one of the easiest constellations that we can use to measure how much of our heritage we still have. It's just important to note, I think, that when we talk about these constellations, they have a history of their own that is special and unique to so many people, and not just the usual Greek mythology that we're familiar with. What I'd like to do now is take you on just a little bit of a tour around Orion. This is something that you can see most of Orion, even in small towns and cities. And we'll start with something that isn't the brightest star, but is maybe the most interesting star, Betelgeuse. Betelgeuse is in the upper left, as you can see. It's a bright orange star compared to the rest of Orion's stars. If you look at the picture, most of Orion's stars are very deeply bluish in color. Astronomers can look at colors of stars and tell their temperatures. So we know by this particular color of orange that Betelgeuse is about 2,500 kelvins. It's about 4,000 degrees Fahrenheit, 5,000 degrees Fahrenheit. It's 643 light years away from us, light year being the distance that light takes or travels in 1 year. It's about 6 trillion miles, so just a long way away. It is 100,000 times brighter than the sun, and yet significantly younger, only 10 million years old, and is probably the best candidate that we know in the sky to have a significant supernova event potentially in our lifetime. To an astronomer, potentially in our lifetime means anytime between tomorrow and 100,000 years ago. The name itself, and most star names, come from Arabic origins, and often they're either translations, transliterations, or mistransliterations, which is the case for Betelgeuse. It's a corruption of the Arabic Yad al-Yaza, which is means the hand of the central one. And sometime during the early centuries of the first millennium, or the mid-centuries of the first millennium, I should say, there was a misprint of Y into B, and that became Beit al-Jawza, which eventually became Betelgeuse. The thing that makes Betelgeuse so fascinating is its size and its potential for destruction. Very few stars are big enough or close enough for us to actually see. If you think about all the things that we know about the universe, they all come from a twinkle of light. Most stars, with the exception of just a handful, cannot be resolved even with the most powerful telescopes. Betelgeuse is an exception. And in the case of Betelgeuse, we can see that it's bloated and distended. It's losing quite a bit of its mass on its way to a supernova explosion. When it does happen, it will be the brightest object in the sky. You'll be able to read, if you're around when it happens, read at night by its light. It will cast shadows on the ground. It's sufficiently far away that we're safe from that explosion. But there was a lot of interest last year, you may have read about Betelgeuse dimming. And in fact became so dim that it was barely visible in city skies. And that's probably because a lot of material was thrown off it. As it ages, most stars, when they age, lose a lot of mass right before they explode. And you can see in this comparison that if you put Betelgeuse in the middle of the solar system, its size, its edge of its surface would extend beyond Jupiter. So it's quite a big, large star. Rigel is actually the brightest star. It's also 10 million years old, about 85,000 times as bright as the sun. Its name comes from Rigel Yaza al-Yusra, which means left foot of the central one. It's the sixth brightest star in the sky. Turns out to be a trinary system, and it's roughly at the same distance as Betelgeuse. Eventually, it will explode in a supernova as well, although probably later than Betelgeuse. The other thing that's interesting about Orion is that most of the stars are about the same distance from the Earth. So even though stars, as they move when the galaxy ages, the constellations are never constant. They're constantly changing. But because Betelgeuse or Orion is so far away and the stars are roughly the same distance, Orion will keep its shape for quite a while, at least the main stars. Bellatrix is the other shoulder. It's called the Amazon star. This is one of the few stars that has a Latin name rather than an Arabic name. It is not especially bright, and by that we mean only 6,000 times as bright as the sun, and only about 20,000 degrees in temperature. So it's about 4 times as hot as the sun, but still quite bluish. And then we have Saiph. Saiph comes from Saiph al-Jabbar, the sword of the giant. This star is the dimmest of the 4 that make up Orion, and it is experiencing a lot of huge stellar wind, a lot of mass loss. It's actually losing about 1 solar mass per million years, and this is another good supernova candidate. It's about as far away as Betelgeuse as well. So we could see in 1 million years, Betelgeuse, Rigel, and Saiph all explode in supernovae, which would be a tremendously different sky than what we see today, obviously. At the head of Orion, we have Mesa, which comes from Al-Meson, the shining one. This is a double star, a bit farther away, 11,000 light years away, but still actually more intrinsically bright than any of the stars we've talked about, 200,000 times as bright as the sun is. And then we have what we call Pi Orionis. This is a group of 6 stars that are all together. It's a loose association of stars. They're all about magnitude 5, which means that you have to be in a pretty dim sky to see them. They make up the shield of Orion if you think about either the ray picture or the Hevelius picture. And then you have the famous asterisms. Asterisms in astronomy are informal groups of stars. Sometimes they take up multiple parts of constellations, and sometimes, often, they are the brightest part of a constellation. Think of the Big Dipper as maybe the most famous asterism that is the set of the brightest stars in the constellation of Ursa Major, the Big Bear. And let's take these one at a time. The belt is made of 3 stars, Al-Natak, Al-Manam, and Mintaka. They are all transliterations of Arabic, meaning the girdle, the string of pearls, and the belt. All about 1,000 light years away from us, and they range anywhere from 100,000 to 300,000 times as bright as the sun. They are hot supergiants. They are also very young, again, 10 million years, and we'll see why this is important in a minute. You also see Sigma Orionis and Eta Orionis. They're interesting because Sigma Orionis is a quintuple star system that is 5 stars orbiting each other, whereas Eta Ori is a quadruple. One of the things that we've learned, even since I was in grad school in the early 90s, was that we've gone from thinking that about half the stars in the sky have companions to knowing that probably all stars have, if not a stellar companion, a planetary companion. The other thing that you'll notice about the belt in Orion is all of that, what we would say as a technical term, fuzziness. Certainly it would look fuzzy in a telescope. And these are gas nebulae, gas and dust nebulae. The most famous of which you can barely see down here is the Horsehead Nebula. The Horsehead Nebula is about 1,500 light years away, and it is an arm of dark dust that sticks out, dust and coal gas that sticks out in front of a more irradiated cloud of hydrogen. You can see on the left your typical picture that you'd see from the Hubble Space Telescope. The image on the right is a more recent image from the Hubble Space Telescope using infrared wavelengths that cuts through some of the dust so we can see some of the detail. This is important because this is where stars form. Stars form in cold clouds that are near hot stars. In fact, the hot stars are the reasons why these clouds start collapsing in the first place. The Orion constellation and the Orion region turns out to be in a very small part of the sky, a nice encapsulation of the life of a star from birth to death. We've already mentioned supernovae. Now we're getting to what some people call the stellar nursery in Orion. If we look just below the belt, you'll see Orion's sword. And in typical viewing conditions, say, even from the campus of Lawrence, it's a little hard there, but you can still see it. You'll see 3 stars. The middle star is something that you'll never resolve. It's always fuzzy, but even a good pair of binoculars can resolve that into a patch of haze and then a group of stars, 4, actually 5, but 4 that we can easily see, called the trapezium. They are dominated by 2 stars, Theta 1 and Theta 2 Ori. I have to admit that astronomers, as creative as we are in drawing these lines, after a while, we kind of gave up with star names and just started using letters and numbers. So we'll have to deal with Theta 1 and Theta 2. But these 4 stars are responsible for irradiating the entirety of what we now know is the Orion Nebula. They are 2 million years old. They have the luminosity of 200,000 suns. They are 30 times as massive as the sun, and they represent some of the youngest stars that we can see. And what I want you to think about when we look at the Orion Nebula, again, this is at the center of the Orion Nebula. It's 1,300 light years away. These 4 stars are lighting up something that's 24 light years across. So lighting up trillions of miles with their own light. And in fact, if we kind of zoom out with this is a VLTI image looking in the deep infrared. One of the things that we've discovered is each of these stars, each of these members of the trapezium are also binary stars. It's what the inset images are showing. And this is what we call a stellar nursery. Sometimes we call it an H2 region. We want to sound like we are self-important. But it is, in fact, where stars have already collapsed and have just been born. And it turns out that the most massive, the youngest stars burn out very, very quickly. It's only ordinary stars like the sun that have a chance to last 10 billion years, as our sun will, and perhaps give the chance for intelligent life to arise. But these young, massive stars, because they're so massive, and because their nuclear fuel runs so quickly, they burn themselves out in just a few million years. And when they do, they explode and they blast away these cavernous, brightly colored nebulae. And in doing so, they collapse the rest of the cloud and dust around them and create things like the Horsehead Nebula, which then starts the process of star formation all over again. So star formation in a very real way is self-propagating. Once you get it started, it will just continue until you've run out of material. And in fact, in the last couple of decades, what we've been able to see with our telescopes is not just star formation, but solar system formation. And this is where my particular scientific interest comes to play. I've been working on the origins of solar systems before the NASA program was called Origins of Solar Systems, plural. These were basically theoretical ideas back in the late 80s. In the early 90s, we started getting hints that there were other solar systems, other early solar systems, and in this case, what you see in the insets are protoplanetary disks. These are all analogs of what our solar system looked like, a disk of gas and dust surrounding a central star in each of these. You can see, for example, a central star in the central image, and they're basically being blown away by the stellar winds from these younger stars. This is how our solar system formed. And in fact, we have geological evidence that a supernova exploded shortly before our solar system formed by looking at very rare radioactive nuclides in meteoritic rock. It's how we know the solar system's 5 billion years old. It's how we know that we formed in a situation, in an environment not too dissimilar from this, where there was probably a very active young star that blew itself apart and then caused our cloud from which we formed to collapse and create the solar system. So as I mentioned, and now here's Orion taking a nap sort of on his side. So you can see Betelgeuse down in the lower left there. One of the reasons why Orion is so interesting and so important is because of the story it tells. It tells the story of the birth, the life, and the death of stars, and tells the origin of us. Even if we didn't exactly come from the Orion star-forming region, this image shows, in addition to the stars, all of the clouds of hydrogen gas and the dust that eventually finds its way into planets and stars, and perhaps other people listening to other webinars or the analogs people in our galaxy. Orion tells our story, just as we tell our stories through Orion. And in fact, you should probably be asking yourself at this point, as I had when I was first thinking about going into this field all those years ago, why, when I look out to find Orion, do I not often see this? This is actually a very beautiful picture of Orion showing what's called the winter triangle. You can use Orion to find your way around the sky, just like you can use the Big Dipper. The belt points to Sirius, the brightest star in the night sky, down at the bottom of the image. And then if you move up to the left, you see Procyon, which is the brightest star in Canis Minor, the little dogs. And the three of those stars put together, Betelgeuse, Sirius, and Procyon, make up the winter triangle. Astronomers were very early on timekeepers and calendar makers. And when you saw the winter triangle rising, you knew that winter was on its way. But still the question stands. If you were to go out tonight, almost everybody here, and look outside, you would not see this. If you were lucky, you'd see that, right? And even then, that image of Orion over a set of English homes looks the way it does because this is a bit of a long exposure photograph. So the reason why we don't see all of what we've been talking about is light pollution. As I mentioned, the night sky shares our heritage, and it is a natural resource. And it's something that we're losing. It's a precious resource above our heads every night that we're slowly losing. The most recent study showed that 1/3 of the world's population can no longer see the Milky Way. When I teach astronomy, I ask my students if they've ever seen the Milky Way. And for the last 20 years, it's been about 10% of the students who have ever seen the Milky Way, our home galaxy. Right now, 2/3 of Europe and 80% of the United States. That is, if you live in the United States, there's an 80% chance that you cannot see the Milky Way from your door. Probably higher in different areas, but on average, we've lost that light or that night because of the light around us. And just to give you some perspective, in the best skies, that is far from cities and in the absence of a moon, you might see 5,000 stars. As soon as you go to suburbs or a small town, you might see 500 stars. As soon as you go to a city, even a city like Appleton, you might see 50 or fewer stars. We are losing our heritage. And so there's a group of astronomers, both professional and amateur, that are fighting to preserve this heritage and this resource. It's not just because our stories are kept in the skies. There are obvious problems with energy use. We light things that don't need to be lit, or use inefficient lighting that spreads light into the sky instead of the ground where we might need it. But it also affects animals and their migratory patterns and their behaviors. It also affects humans. There's been some evidence that shows that our own patterns and our own biology is disturbed by the continual loss of the night. And so the International Dark Sky Association, of which I'm a member, has been working across the world to preserve our heritage and our resource. And there are a number of things that we can do, starting with using efficient lighting and thinking about what we light, and going all the way to a different kind of ecotourism. There are tourism spots in India now where people can go just to go stargazing. And while that may sound a little far-fetched, not so long ago, 5 years ago, I decided to spend New Year's in Panama. Now, I'll admit that some of that was because it was going to be 95 degrees at the end of December instead of whatever it was here in the Fox Valley. But the other part of it was that I wanted to see the Southern Cross. And I saw it my first night. That is a shaky picture I took balancing my iPhone for a long exposure photograph off the rail of my hotel room. But I cannot tell you the excitement I felt in seeing new stars for the first time since I was 13. And I think that there are people, and I think we all could benefit from that kind of experience. In addition, you can help. You can help measure how dark the sky is so that people can come together and come up with common sense solutions that help preserve our heritage and preserve our night sky. One easy way that you could do it right now is to use this little diagram. We've been talking about Orion, and you see 6 different pictures of the stars in Orion, labeled 2 through 7. Those are the magnitudes of the stars in Orion. So in the first picture, basically anything that's brighter than magnitude 2 is visible. That's what you would see in say Chicago or New York. 3 is what you would see basically in Appleton. You can see down to maybe magnitude 3. By the time you get to 4, that's what I can basically see from our own home on a good night. 5, 6, you have to be really, really far away from the kind of light that would disrupt your viewing of the night. And I've included in this little finder's diagram, but really, if you wait until about 9:30 local time and step outside and look east, you'll see Orion high in the east, those beautiful, faithful stars. You'll know you're looking at the right thing if you see Mars just a little bit higher away from the horizon. So this is something that you can do with yourself, your friends, your family. The other thing you can do is to go to this link that I've provided, the Globe at Night, www.globeatnight. And you can actually download an app for your phone and measure the sky brightness. Short of that, you can identify constellations, and it varies from month to month. This month it was Perseus. And you can then upload, you can be an observer and upload your observations. So if we zoom in here to the Fox cities here, you have a couple of my observations and just a couple of other observations. We need your help. Knowing what we're losing helps us fight to get back what we've lost and to get some of that night sky back. Because in the end, No, I move this back. In the end, I want the next 13-year-old who walks out into the snow on a suburban winter night to feel that awe and that connection to something bigger than she is that I had those many years ago. Thank you so much for your time, and I'll be happy to take your questions. Oh, here we go. Sorry, I had a couple of different chats open. I have a couple questions in chat. What are some of the things that we can do? Eliminate the use of LED and maybe halogen. Yes. There's definitely a move to eliminate the use of halogen light and bright LED lights. The main thing with outside lighting is to put it where it's useful and to have it on when it's useful. So not having the acorn style streetlights. So one of the things that the IDSA is not trying to do is make things more dangerous, right? There's clearly the understanding that we need light for safety, but we can have that light if the light is directed downward. We can also certainly rethink why we light buildings at night, right? Why are some buildings lit up at night, and how much energy and how much money are we using to do that when that contributes to the background light that we see? How do satellites affect this? That's a really good question. Normally, satellites don't affect this too much, but Mr. Elon Musk is determined to be a Bond villain by launching multiple constellations of his own satellites, which are highly reflective and do disrupt the night sky for professional and amateur astronomers. Let's see, how is the clarity of the night sky in Door County versus Appleton? It's much better in Door County, I would say. Now, I should back up because there are quite a few questions about the different conditions. What we need from all of you is to help us collect data. What I have are my impressions. So I know that while I haven't made the measurements at Bjork London, I know it's quite dark. In fact, we've often when we want to do good observing for our students, that's a good place for us to go. But we definitely need more information in terms of what can actually be seen in different parts of the state. International Dark Sky Association is actually not well represented in Wisconsin. So they are absolutely looking for more members. So outdoor lighting should be shining downward, right? Illuminating a path and shielded. Are dark skies have already been created in the Midwest or are more developed? Yes, I think more are. I'm not sure what the number of the dark sky sites that are being created. There are some dark sky tourism places mostly in the West, right, in the Mountain West. Best places to see the Milky Way. I got a question from my dad. Best places to see the Milky Way in the U.S. would be anywhere away from lights. So back in the Rockies, Dad. So go back to Colorado. But basically anywhere you can see a sky where you don't have a lot on the horizon, and choose the best time. So it turns out that the winter sky and the summer sky are the two best skies to look at stars, and that's because of where we are in our galaxy. We face towards the center of the galaxy in the summer, and we face along the disk of our galaxy in the winter. In the spring and in the fall, we tend to face out of the plane of our galaxy, so we tend to see fewer bright stars. So if you want to see the Milky Way when it's directly overhead and its brightest, you want to look in, say, December or January, or in July and August. That's when the Milky Way is easiest to see. Having said that, astronomers love the winter because the seeing, which is the stability of the atmosphere, is best in the winter. And unlike most people around the planet, astronomers love the long nights. I get depressed when I see that the winter solstice has come around and we're starting to lose our night skies again. So if you want to see the Milky Way, your best shot is January in the northern hemisphere, someplace far away where it's cold and the air is clear. Yes, I have considered, and I will, especially in terms of using students for collecting data. And this was also an idea that I had with the Bjork-London class. At one point, we were thinking about holding the Bjork-London class remotely. We were trying to think of different things that we could do with the Bjork-London class. And we will do this with my astronomy class in the spring, which is wherever the students are, they can do observations, not just of sky brightness, but also astronomical observations that require long baselines. So something that you can do with friends as well is if you have somebody who lives in Wisconsin, somebody who lives in New York, and somebody lives in California, the three of you can look at the moon at the same time. And by noticing how far away it is from a bright star, you can calculate how far away the moon is. This is a technique that ancient astronomers used and was able to determine the distance to the moon without much in the way of technology. Is there any prospect for predicting more precisely a Betelgeuse supernova? My colleague Matt from Germany, thanks for joining. Not really. What we look for certainly is extreme mass loss. We know that massive stars that are about to supernova go through several series of mass ejection events. We can also look for what's called dredge-up events. So stars shine because of fusion, and as stars age, they fuse different elements. Some stars get highly convective, so their surfaces can actually dredge up the material that's being fused from near their cores. And we could look at a star like Betelgeuse, and if we notice that it had higher abundance of, say, silicon or neon or carbon in its atmosphere, that would be an indication that it's close to supernovae. But in terms of being able to narrow it down any closer than 100,000 years, I think we lack data. The other predictor for a supernova event is a burst of neutrinos, but that happens just prior to the supernova event, or actually as it's happening, the neutrinos reach us. Let's see. How far do we feel the effects of light pollution from bigger cities, say from Chicago? Oh, hey, Nick, how you doing? I got a former student there. So it impacts for quite a distance. If you get away from Chicago, you'll see a glow on the horizon, but even a little bit of distance will buy you better skies. And I'll give you a good example of this. I used to, when I lived in the Bay Area, if you went to the headlands just north of San Francisco, even though the lighting wasn't great, it was better if you shielded yourself from that glow near the horizon. Now the horizons are always going to be awful, but you can, if you get some distance between you and in a city, 20 miles or so, that definitely helps. Let's see. Why do many stars, okay, this is an excellent question. Why do many stars come from Arabic names? So the reason why it has to do with the preservation and the development of astronomy, basically after, if you like, the fall of Rome, with what we would call Western classical ancient astronomy and physics fell. Many of the work did find its way to Persian astronomers, where they not only preserved some of the things that, say, Ptolemy wrote, but they expanded upon it and did much of their own work. In fact, I had a student working with me. I thought she was going to be here. Sabrina is here. Where we were looking, one of the questions we were asking was, when was the first time astronomers noted the colors of stars? Stellar catalogs have a long history of people noting how the stars are different brightnesses. We starting with Hipparchus, and probably even before, but Hipparchus was one that at least has a surviving method of categorizing the stars. But what we found was interesting was that very few astronomers, ancient astronomers, wrote down the colors of stars. And it turns out that, as far as we could tell, the first real catalog of stars that included colors was from like the 9th century after our current era by a Persian astronomer. And then there are some star maps in some Native American star maps on skins that include star colors as well. So the answer to your question is that with the loss of some of the Western knowledge and data, Persian astronomers rose in importance. And then that information was moved back, or found its way back into Western, or into Europe, and was added to translations, or was kind of folded into the knowledge base of medieval Europe. And as a result, the stars were known by, I mean, the stars themselves, right, have always been known by different names, by whatever culture named them. The International Astronomical Union decided to recognize the contributions of Persian astronomers in particular by using those names that many of which were in common usage. Let's see. What quality telescopes does LU have for faculty and student use? We have a few telescopes that are, to an astronomer, the size of the telescope is everything. And the size, we mean the size of the piece of glass. And we have a 10-inch and a 12-inch telescope. 12-inch telescope is a relatively new addition to the department, but sadly, the pandemic has contributed to us not using it yet. Hopefully, things will be in a position where, even though I'll be teaching the astronomy class remotely in the spring, we'll have public observation parties with the telescope using software, so we can display what the telescope is seeing on a screen, so that we can still be socially distanced. Let's see. Does the global fascination with Orion come from primarily correlation winter? Or is it distinctly bright? I think that there are a number of things. I think that it is a winter constellation, and I think that is part of it. And you have to remember too that when people were setting out the original notions for these constellations, whether it's European or China or Indian or anywhere else. The first observations were done in very dark skies. We didn't have the cities or the city lights that we have now, so they noticed things. And Orion is not only bright, but it's fairly compact. And in terms of looking like a human figure, it actually kind of looks like what it's supposed to look like. But it's interesting too when you think about as soon as I read that the belt of Orion was the spine of a bison, that makes sense given the rest of the stars. When I read about the belt and the sword of Orion being kayaks, I could see that too. But so I think it's bright. I think it's big, but not too big, so it's not spread out. And also, don't discount the Orion Nebula, this fuzzy patch. You can see that with your naked eye. Its magnitude is about magnitude 4. So assuming there's no haze and there's no light, you can see this star forming region that's 1,500 light years away. That's a few quadrillion miles away from us, where stars are forming, where planets are forming, and where stars are about to die. Let's see. What else we have here? I want to make sure I get to all of these questions. Yes, why does Subaru use the Pleiades? That's awesome. Subaru is the Japanese name for the Seven Sisters. That is precisely why Subaru has that pattern. Astronomy is everywhere you look. Thank you for reminding me that. Yes.
I was going to say thank you, Megan, for catching up on all the questions in the chat. We had a little bit of technical difficulty for me to get back on. If anybody has any last minute questions, we could wait a minute or two. I think we're all caught up.
I'm sure I missed some.
Oh.
Can I provide some additional gear, apps, websites? Yes. Is there a good way that I can maybe submit that somewhere?
I was going to say, yes, if you send us a list, or we can include it in the follow-up email.
Okay. Any pop culture hot takes? Oh, so I'm a Star Trek fan, not a Star Wars fan. I mean, I like Star Wars, but I like Star Trek, I have to admit. But when you get down to it, one of the things that I really liked, I have to admit, if I'm going to be very, very nerdy about this, is Battlestar Galactica, the more recent Battlestar Galactica. And the main reason why I liked it, I mean, there were a lot of reasons to like it, but in one critical episode, the main starship jumped close to Earth. They're outside Jupiter, I think. And the star field includes Orion.
Oh, cool.
Correctly. And also there's an episode of Dexter where he's doing his thing with his boat, and above his shoulder is Orion.
Orion. So. I do remember that. I am a Star Wars fan, so.
Well, we can all coexist.
Right, exactly. We can all share the universe, right?
Yes, right.
Well, it looks like we're all caught up again. Thank you so much for your comments and sharing your time and talent with us, Megan. I want to thank everyone for attending today's Learning at Lawrence event. This is our last Learning at Lawrence of the fall term. We'll be planning for the winter term soon, and to learn more about the Learning at Lawrence series, check your email, follow us on Facebook at Lawrence University Alumni, or check out our website at lawrence.edu/alumni. We also record many of these webinars, and we have them on our YouTube page, so be sure to check that out. But until next time, continue to learn, continue to lead, continue to be the Laurentians that you are, and be the light. We will see you in 2021. Thank you so much.